בוקר טוב לכולם, אנחנו נמתין עוד כמה דקות למצטרפים נוספים ונתחיל בוובינר. Mohamed?
I'm here.
Hi, we're waiting for some more participants, and we shall start in about 2-3 minutes.
Perfect. Super. Thank you.
Okay. שלום שוב לכולם, אנחנו נרצה להתחיל תודה קודם כל שהצטרפתם. אנחנו נרצה להתחיל את הוובינר השבועי שלנו שיעסוק בכלים השונים להערכת מצבם של שנאים ומדידת חיי השנאים. נמצא איתנו מר דוקטור מוחמד חליל מחברת דובל, הוא הטכניקל אפליקיישן אנג'יניר שלהם, ואני אשמח כמובן, אנחנו נשמח אם יהיו שאלות שתרשמו אותם באופציית הצ'אט, והוא ישמח לענות בסיום הוובינר, ואני אפנה אליו עכשיו באנגלית כדי שהוא יציג את עצמו ויתחיל את הוובינר. אז תודה שהצטרפתם ושיהיה האזנה מהנה. Mohamed?
Yes.
Okay, we shall start. Present yourself and you can start.
Thanks, Eddie. So my name is Mohamed Khalil, and I'm a technical application engineer working for Doble for more or less around 4 years. And I'm covering EMEA, providing support for all the asset management products, and providing trainings, administration, and consultation services. So I hope all of you are staying safe and healthy. The topic that I'm going to present with you today is the asset management of power transformers in electric utilities. And I will just, in this quick presentation, show to you a new approach that is somehow being used in many electric utilities. And this approach is called health index approach. It's a nice approach that will enable you to aggregate all the information, all the test results that you have with power transformers and provide you with just an index, and this index will help you to judge the condition of your transformer or any asset in general. But in this presentation, it will be more focused on power transformers. So for the agenda, we will start with the importance of the asset management of transformers and the current challenges nowadays. And from there, we will see the available diagnostic methods that we can utilize in order to assess the condition of our transformers. These tools or these methods, they can be online, offline, or in service testing. We are going to see the difference between each of these methods together. The point is that these diagnostic methods, they are very helpful, but they will generate large amount of data. So we will see how we can make use of this data using the health index approach, and how we can use this approach to prioritize our maintenance activities, and of course, mostly important, to allocate our budget of maintenance or deferring replacement, efficiently on the short and the long term. And we will see also how we can develop a health index for our assets, and what are the different techniques that are currently used by the electric utilities nowadays. So if we will speak about the challenges, the major challenge now when it comes to the power transformers is the number of the age of, or the number of the average age of the transformers that are in service. This number is increasing, and at the same time, the replacement cost of these old transformers is too high. And power utilities, they are facing a continuous increase in the load demand. And this results in more failures and a high failure rate. According to the most recent SIGRAE survey that was carried out in 2008, they found out that the failure rate of the substation transformers is around 0.0057 failure per unit year. And this means that if you have a fleet of 100 transformers, you will probably will have around 9 transformers with major problems within 15 years. So this means more or less 9% of your fleet will have major problems. And the other challenge that faces the electric utilities is the cause of the failure of the power transformers. Power transformers cannot be considered as a single element or a component in the network when it comes to the failure analysis. Just as an example to that, I brought here a slide from the ISO 18095, and you can see here, I will bring my laser pointer, that the transformer is divided into a number of components. You have the winding, you have the core, connection, pushing, cooling system, and tap changer. And for each of these components, it has its own failure mode. You have the dielectric faults or the dielectric failure mode, and they are divided into a number of failure causes. You have the same for the thermal fault and the mechanical faults and the external faults. So when it comes to the failure of power transformer, there are many failure causes for the transformer failures. In addition to the different reasons of the transformer failures, utilities are now forced to optimize, to reduce the life cost of the power transformers. Therefore, many utilities, they are changing their maintenance strategy that was used to be the time-based maintenance for a long time to the condition-based maintenance. So in the past, with the time-based maintenance, all what you need to do is just to analyze some offline electrical test results. But nowadays, with the available online condition monitoring systems and the quick, rapid development in the IT and the technology, the outcome is a huge volumes of data that need to be analyzed. And it's very hard for any transformer expert to take a decision, an action based on a single diagnostic test. So there is a need for a quantitative indicator, such as the health index, to describe the condition of each transformer based on all the available data. So as an example on the importance of the asset management, I took this slide from one of the SEGRE technical brochure, and it's just described here an experience from the Japan National Grid. They decided to put a long-term plan for the old circuit breakers in their network starting from 2009 till 2048. And when they put this plan to replace the circuit breakers, they found out that the number of breakers to replace per year is not constant, and it changed significantly. And this, of course, will result in a variable allocated budget per year, which can be a nightmare to any asset manager to deal with. So they followed a different approach. In order to replace the old circuit breaker in Japan, they decided to divide these circuit breakers into a number of categories based on the risk. So there are circuit breakers with low risk and the replacement was deferred. There are circuit breakers with risk priority 2 or risk priority 1, and the replacement is going to be prioritized. And the high risk circuit breakers, and these will require a quick replacement as soon as possible. Of course, the calculation of the risk is based on the available data, but when they followed this approach, they were able somehow to have a smooth replacement plan, as you can see here. And this just to show the importance of an efficient asset management and having more or less efficient tools that can help to manage the data and evaluate the risk. So back to the point of the condition-based maintenance and why it helps to optimize the life cost of the transformers. The time-based maintenance, the old traditional approach, is usually done at fixed intervals of time, which more likely determined by the manufacturers who design the same product for a large range of users. And at the same time, this product is operated in different operational and environmental conditions. And the manufacturer still put its recommended maintenance interval according to the worst case scenario. So in the end, you as a user, you will find that you are doing unneeded maintenance activities according to the worst case scenario, of course, that is put by the manufacturer. And this means higher cost, more labor, and a high possibility to have induced failures because you are doing simply unneeded maintenance activities. In this graph, I just showed here that if you have a small maintenance interval, okay, you are going to have the total cost is going to be quite high. And this total cost is going to decrease as you increase the maintenance interval till you reach to the optimum maintenance interval or the best interval of interval time where you can do your maintenance. After that, if you are going to be late, right, the total cost will increase because the possibility to have a failure or an outage is going to increase. So the majority of electric utilities now, they are looking forward to achieve this optimum maintenance interval through the condition-based maintenance. There are tools to do that, and these tools can be categorized into online monitoring, and these include permanent installed sensors on the transformers that can do the continuous monitoring. And we have also the inline testing, and the inline testing, they are just non-invasion assessment that can be done while the transformers are in service, such as the oil sampling or the Ph.D. surveys. These two approaches, the online monitoring and the inline testing, it's very important that they should be supported by the offline testing. Again, with these approaches, we are going to have a large amount of generated data that should be assessed, that should be somehow stored in a proper way. We are going to see that together before we apply the approach of the health index. So for the condition-based maintenance and the strategy to implement it, it's a simple one, and it's available in details in the SIGRAE technical brochure 660. So the idea is to start with the inline diagnostic tools and the online condition monitoring in stage 1 here. And in case there is any abnormalities, any unexpected increasing trend of the measured data, we can go for the forced outage, right? Take the equipment out from the service, do the offline testing to confirm your findings, and then decide the next step, okay, which can be here. Or if everything is fine, everything is good at stage 1, we can follow normally the planned outage for the maintenance directly in stage 2B. The most important thing here is that at any stage, we need to archive the data, which can be online, inline, or offline. And with this archived data, we need to make use of it in order to help us for prioritizing our maintenance activities. So if we will speak about the inline tools very quickly, the most famous inline tools when it comes to the power transformers, visual inspection, the most easy one, we have the partial discharge, and we can do a simple routine BD surveys. There are a number of equipment that can be used to do the BD surveys. The simplest one is something like that here, and it's just an instrument that can detect BD based on the radio frequency interference. And we have the thermal imaging to detect any hotspot, and of course the routine oil sampling that we are all doing from time to time from the power transformers. For the online tools, these are the permanent sensors that we are putting on the transformers, and we can monitor through these sensors the condition of the bushing by placing a sensor to measure the leakage current. And we can also consider the partial discharge sensors that can be used to detect any BD activities. And of course, some sensors for the DGA to measure the dissolved gases inside the oil in the main tank, and if needed for the tap changer. In addition to these sensors, there are the operational parameters like the loading, voltage, and temperature, etc., to have a complete view on the health operation of the transformer. So this slide just to focus more on the power factor of the bushing and how to measure it online. Usually we are measuring the power factor of the transformer through the offline testing. So the transformer is out of the service, and then we are applying a voltage on the bushing, and we are measuring the leakage current through the test tab. In the online condition monitoring, we cannot apply voltage. So we can measure the voltage that is coming from the voltage transformers of the transformer circuit. And so we are having the voltage from here. We are measuring the current through a sensor that we are putting it permanently on the test tab of the bushing. And we can measure the phase angle between the measured voltage here and the measured current here. And we can also measure the capacitance from the measured leakage current. So we have the online power factor, we have the online capacitance 24 hours a day. Any deviation, of course, from the normal operation, we will need to move to the offline testing. For the BD sensors, we have a number of sensors like the UHF drain valve probe. It's a sensor that can detect the BD that can happen inside the transformer. You are just putting it through the drain valve of the oil. And we have a split core of high frequency T or HFCT. We can put it around the neutral to detect the BD that can go through the ground, and also the many high frequency Ts, and these are used to detect the partial discharge that happen at the bushing. So we can see here the sensor that is measuring the leakage current and the cable, and this cable is connected to these high frequency Ts to detect any BD spike in the leakage current. And here are the DGA module measurements, the Callisto group. It can measure up to 9 gases. So in the end, the most important thing, you are going to put, of course, sensors on each transformer or the transformers that are somehow critical in your asset. The most important point here is to have the possibility to access all the measured data remotely, and it can be done through the web interface system. So in this way, you'll be able to have an overview on the trending data of all your assets. You can have, for example, the measurement of the BD of the bushing from this transformer. You can compare it with the BD measurement of another bushing from another transformer and see if there is any abnormalities in the increasing trend, and so on. So the most important from the online condition monitoring system is to aggregate all the data, centralize these data in a historian or a database storage that you can have an easily access to it. When it comes to the electrical offline data, there are several tests that can be done when the transformer is de-energized, like power factor and capacitance, excitation test, leakage reactance, SFRA, turns ratio, and DC winding resistance. And each one of them has its own purpose in order to do the diagnosis of the transformer. So here is a case study for a transformer, 48 megavolt ampere, that was manufactured in 1984. And this case study will just show how the results of the offline, online, and inline tools can be used to get together to confirm your findings before you decide to open a transformer. So in this case study, the client here was using an online DGA system, and this online DGA system, it detected a sudden increase in the composite gases. The composite gases here were hydrogen, CO, C2H2, and CH4. And when this sudden increase in the DGA happened, there was an alert that came out from the system. It was a prime system, double prime system. And the second step with the online data, when it shows that there is abnormalities, they decided to take an oil sample. So with an oil sample, we are speaking about in-service testing. And when they did the online sampling, they found that the value of the overall composite gas was quite high compared to the previous one. So at this point, the client decided to take the transformer out of service for the offline testing. In the offline testing, the power factor and capacitance didn't show anything abnormal, okay, when it compared to the measurement taken before in 2018 and 2016. But when they did the DC winding resistance test at the low voltage side, there was a significant difference in the measurement of phase B compared to phase A and C, and this difference didn't exist in the previous test sessions. So the decision in the end was to go further, open the transformer, and do a visual inspection. And when Doble did this investigation, we found that the middle phase insulation was damaged, and this was the cause of the unexplained DC winding DC winding resistance, and of course the sudden change in the dissolved gas analysis that was detected by the online monitoring. Another case study, GE auto transformer manufactured in 1986. In March 2008, a client decided to install an online monitoring system. It was also double prime, to monitor the online power factor and the capacitance of 345 kilovolt pushing. After 3 months, in July 2008, they found out that there was a continuous increase in the measured power factor of this pushing. The daily, weekly, and monthly power factor were increasing, and the same also was for the capacitance. There was a continuous increase in the capacitance values. So the decision was to take the transformer out of service and do offline testing. And they found out that the power factor was 1.36, and it was quite high compared to the previous test session and to the nameplate value. So they did another diagnosis. They took an oil sample from the pushing, and they found a very high value for the hydrogen, 6020, and a low value of the acetylene, around 0.9 ppm. In pushings, this is an indication to a partial discharge. So the decision was to go ahead and do a forensic examination of the pushing, and they found the burning in the foil and, of course, symptoms to the PET. So the idea from these case studies, again, to show how efficient can be the online monitoring system if it is supported by inline and offline tools to confirm your findings. It's also important to have a look on the current test session of the offline test data and compare the results with the previous ones to detect any deterioration symptoms. So this means that electric utilities have to centralize and digitalize their database of the historic offline test data. In this way, they can compare the current test session with the previous one to detect any deterioration symptoms. So in Doble, when we consider that, we put in our mind that once the data are taken in the field, it is possible that the user, once he finishes the testing of the power transformer, can upload the test results directly to the database center, which can be accessed anywhere inside your organization. And later on, when the testing team is going to test the same transformer again, they will just need to download the test file to the laptop or to the dock. It's just a tablet from Doble that has some specification. And in the end, they will be able to have the same test file again, and they will go to the same transformer. They will not put the nameplate data or anything. They will just do the new offline testing and again re-upload the test file. With this closed loop, there is a very low possibility to have any kind of human mistake in the data entry. And of course, it will allow a centralized database for the offline testing. In the end, you can extract the offline testing of any family of transformers in your fleet. You can simply select here what transformers you want to extract. So I can select 2 winding transformer, and here what test results you want to display or extract. I can select, for example, overall test, which is a power factor, excitation current, tendency ratio. Okay, and here what parameters from this test you want to display. So I can display, I want to display, for example, the kilovolt ampere of the transformers, the type of the cooling of the 2 winding transformer, and also the power factor measured value. And you can extract these values, you can do your analysis, you can do a comparison for the transformers from the same manufacturer and see if there are any kind of deterioration symptoms. So this was for the offline data. So once you have all the transformer data available in a digital format, you can go ahead and apply the health index approach. And the health index approach is a method, it's a technique to combine all the information of the transformers in order to have a single quantitative index that can express the overall condition of the transformers based on the available data. So how this will work out? Each diagnostic method will be given a weighting factor, and this weighting factor is based on the importance of the diagnostic method. And each test result will be given a score based on a predetermined limit of each test. We will see that in details. But in the end, the asset health index will be equal to the weighting average or the weighting sum of the assigned score and the weighting factor. There are other methods, of course, that we will see also in the coming slides. For more details on the health index method, one of the useful documents in this aspect is the SEGRE Technical Brochure 761, and it discusses in details the different classical methods on the health index approach. So with the health index, it will be a method that will enable you to evaluate the condition of the asset in a consistent way by applying the same rule The available data can be online, offline, operational, can be through the visual inspection. One of the things that is quite important is to give a meaning to the health index, to the value of the health index. So if you have a health index of 2 or a health index of a value of 10 or 30 or 50, what does these values mean? So for this reason, the health index range can be divided, as an example, to a number of sub-ranges here, and each of these sub-ranges can be given a description to describe the condition of the transformer. So from 1 to 3, we can say it's good. From 3 to 10, it's deteriorated. And here, the condition is somehow require investigation. And finally, from 30 to 100, the condition is somehow bad. These definitions, they came from the SEGRAY working group A2.43, and good is always assigned to transformers with online and offline test data that are within expectations. And the deterioration or point X here describes a transformer whose data changes but not significant. Point Y or investigation reflects a significant change in the transformer data that require an understanding of the cause. And finally, point Z. And point Z, it means that there is something bad is happening with that. The test data shows that they are no longer accepted and they require an immediate shutdown of the transformer. So in this way, we can give to the health index values a meaning if we can categorize the values and describe each of these categories. So once you determine the health index of the transformer, you can evaluate the associated risk with the transformer failures. If you remember the example of the SEGRAY on the Japan experience. So in order to evaluate the risk of the transformer, risk is simply a function of the probability of the failure and consequence of failure. Consequence of failure can be interrupted megawatt, customer interruption duration time, repair time, or the replacement cost, etc. The consequences of the failure, they are different from one utility to another, but they are very well defined in each utility. So to evaluate the consequence of the failure, it can be done easily. There might not be somehow challenges in that, but with the probability of the failure, the traditional way is through statistics, and it's a long way and a lot of assumption. The easy way to evaluate the probability of the failure can be through the health index. If you have a transformer with a bad condition, it means the health index is high, and so the probability of failure is going to be also high, and vice versa. Good as health index mean good condition and low probability of the failure. So this is just an example that show how we can correlate the health index score with the probability of the failure. As the health index score is somehow low, probability of failure is low. The health index is going to increase, the probability of failure is going to increase exponentially. So just as a summary, here on the point of the health index, you have a lot of data. All of these data will be combined together to give you one value, which is the health index. And from this health index, you can evaluate the probability of the failure, which is needed to evaluate the risk. You will need also the key performance indicator. You will need the risk framework in your company to evaluate the consequence of the failure. So the risk can be calculated here. You have the S-health index, you have the S-risk index, and from these both, you can take your decision to replace or repair or refurbish. But the challenge here is that your decision is always limited according to the allocated budget and the planned budget. And so you may need to do a prioritization based on these two values here. Just as an example on how the health index can be taken or can be used to provide management decisions. If you have a health index from 0 to 25, you can consider normal operation and preventive maintenance. But if you have a health index from 90 to 100, in this case, you may consider immediate shutdown. In between, you can consider restricted loading operation and more oil sampling and more other actions. So we spoke about the asset health index and its important and how it can work and how it can manage the data. So the question now is how to develop the asset health index, or how we can create a health index for your asset. The first step is to identify the purpose or the objective of the health index. Is it to prioritize the maintenance activities or to do a replacement for your asset? The second step is to break down your asset into a number of subsystems and define for each subsystem the failure modes. And for each failure mode, identify the possible diagnostic methods. So we have asset, divide them or do a breakdown to subsystems, and identify for each subsystem the failure modes, and for each failure mode, identify the diagnostic methods related to the failure modes. So in another way, if we can look here, we have a transformer. We divide it into a number of subsystems here, and for each subsystem, we define the related failure modes, and for each failure mode, we have the source of the data. It can be online or offline, etc. So these data, they will simply go through analytics, and these analytics, they are built up according to the latest standards. They will just convert the values of these data into scores. And then at this point here, you have scores. Each group of score will combine together to give only one value for each failure mode. And then each group of failure modes will combine together. The score of each group of failure modes will combine together to give a score for each subsystem here. And finally, the scores of the all subsystems will combine to give you the health index score. Okay. While we are dividing the asset into a number of subsystems and identify failure modes, and we consider the group of analytics, the reason behind that for you as a user, when you can easily identify the reason behind a high health index, okay, or find out why this transformer condition is not good. As an example here, if we have here a transformer, it has a high asset health index here, so we can look here to the different subsystems. We can say, okay, we have the bushing is quite high, so it means the condition of the bushing is not good, and the insulating material, which refer to the DGA and oil quality, also doesn't show a good condition. Here, when you click, or let's say on the insulating material, you are going to see the different failure modes. We can say here that the thermal fault arcing, because it's high, so it means that C2H2 is somehow high, and also the dissolved gas anomaly, the total dissolved combustion gas are quite high. We can even go to a lower level, and we can look at the different analytics, the different standards, and identify why this transformer here has a high asset health index based on the lowest level of analysis. Okay, so the last point is the techniques that are used to evaluate the health index. There are several techniques, and the simplest approach is the worst case scenario here. This is the most easy one, and in this approach, each failure mode is given a score based on the associated data, and the health index will be equal to the worst case scenario. From experience, this method of the worst case scenario is not that effective, as you cannot differentiate between a transformer with a single advanced failure mode from a transformer with a multiple advanced failure mode. In the end, you are going to have just one value, and this one value will be equal to the highest or the worst failure modes. But you will not be able to identify how many failure modes have a bad condition. So the S healthy index, or the worst case scenario, is not always the recommended way. The other approach, which is quite famous in the industry, is the weighting approach. And with the weighting approach, you simply apply to each diagnostic method, or you give to each diagnostic method a weight and give a score to the test results of each diagnostic method. So as an example here, you have the scores of two test results, 30 and 10, right? In order to combine them together, you have the weight, and this weight show how important each test compared to the other. So to combine them, we just multiply this value by this value plus this value by this value and divide by the summation of the weights in order to have one single score for the failure mode. The same on the failure mode level. To combine this, the score of this failure mode with the score of this failure mode, we do the same, multiply the score by the weight and sum them together. So this by this plus this by this and divide by the summation of the weight to have one score here. And you do the same with the subsystems to have only one value of the S health index. It's very simple, easy to implement, and that's why it's quite famous in the industry. However, the weighting factors for the diagnostic tests here, right, they are based on the experience of the expert, which can be different from one person to another, and this may cause or create a sort of disagreement. So another drawback of the weighting method is overlap of the scores that can happen because we are giving the scores based on exact values. So as an example here, let's say that the hydrogen according to the IEEE is divided into a number of categories from 0 to 100, 100 to 700, etc. And each of these categories you are giving a score. So if the hydrogen is from 0 to 1, so it has a score of 1, but if it's quite high in thousands, it will have a score of 5. The point is, when you are going to have a hydrogen with 95 ppm, you may suddenly say, okay, 95 ppm, it means that it's here, so the value will, or the score will be 1. But if you will consider the accuracy of the measured sensor, and the accuracy can be something in between, let's say, positive or negative 10%. So you are speaking about a true value somewhere between 85 and 105. So now we are not speaking about true value, we are speaking about confidence level. So your score can be 1 or it can be 2. You cannot exactly determine either it's 1 or 2 because the true measurement, the true value doesn't exist according to the uncertainty theory. So this is one of the other challenging thing with the weighting approach. The other drawback of the weighting method is the score dilution. And with the score dilution, the idea behind it that the weighting method may neglect the influence of a bad diagnostic test result on the overall health condition. So you have here 4 diagnostic methods, and the 4 diagnostic methods, they have different scores starting from 1 up to 5, and 5 means very bad. And this diagnostic method is somehow, it's 5. It's very bad results. And you have the weighting of this method is 5. So it means that it has the most significant impact on the health index. But in the end, you are going to find that the health index is equal to 3. So it means it's good. So the health index showed to you that the condition is somehow good, although one of the diagnostic test is very bad and its impact is the most significant. So recently, the electric utilities, they are somehow looking forward to develop the weighting method, and some of the new approaches that are being done is to consider the fuzzy logic approach. And with the fuzzy logic approach, it's divided into 3 steps. The first step is the fuzzification, and the fuzzification, you just turn any value to convert it to a fuzzy value, something between 0 and 1. And we use for that the membership function. So you have the true values. These true values will be converted into a fuzzy set or fuzzy values from 0 to 1. And they will go through a built-in fuzzy rule engine. And this fuzzy rule engine, it consists of a lot of if and then rules. And these if and then rules, they cover all the possible scenarios that can happen with the transformer based on the available test data. And in the end, the fuzzy engine rule will give you one value, one health index value, of course, and this value will be converted again from the fuzzy set value to be a true value through the defuzzification. So with the fuzzy logic method, it's based on if-then rule, which is constructed, of course, according to the experience of the expert. There is no weighting is needed. It doesn't apply sharp thresholds between the grades of the input data. And one of the most important things that fuzzy logic is considered as an artificial intelligent method because it does, and at the same time, it doesn't need a training data. So this is one of its strong features that can process the rules, and it can provide all the possible scenarios and form accurate decisions without the need of a training data, just on based on the rules. So the only drawback with the fuzzy logic is the very high complexity of these methods. So just as an example here, this is a complete fuzzy logic model to evaluate the health index of the transformer based on the DGA data and also based on the oil quality data and the electrical data here. You have the capacitance, leakage reactance, internal ratio, DC winding resistance, and also some operation history, load factor, and the heat stress. And the built-in rules for this model is around 560 rules. And to adjust these rules, it takes time. So this is one of the drawbacks of it is the complexity. Another techniques for the health index is artificial neural network. The artificial neural network, or ANN, it consists of a layer of input nodes and usually one layer of hidden nodes and an outer layer. And between these layers, there are the connecting weights. And all what we need to do is to do a training here. So this method will require a training to require data that should be structured in a certain way and run on find out the best values for the connecting weights. Another similar approach to the artificial neural network is the ENGIS, and I put a block for it here. And this ENGIS is an abbreviation for the Adaptive Neurofuzzy Inference System. It consists of 5 layers. It's a combination between the artificial neural network and the fuzzy logic. So the first layer is always related to the inputs. The second layer is for the fuzzification, where the fuzzification is being done. The third is for the rules layer. You are putting all your rules here. And the fourth one is to normalize the calculated firing threads that are coming from the rules. And finally, the fifth layer is the defuzzification, where you are going to have the value of that health index. So this is more into machine learning, the artificial neural network and the ENGIS. And they are not popular in the industry for the time being, because The training data should be in large amounts. It should be a good structured data. The second thing is that what we are calling it a symbolic reasoning. And the symbolic reasoning is the inability for the user to understand why the health index is good or why it's bad. With the previous method, he can go to the lower level and understand why the decision was taken like that. With the artificial neural network and machine learning, this is not possible because the output here is based on the training data. And usually in the industry, when decision is taken, people like to know that this decision will be taken based on a certain reasons, not based on a training data or things that are not known. So as a conclusion here, the degradation of the power transformers is a complex process. There are many parameters needed to assess the condition of the transformers. Since we have large amount of data, the health index approach can be helpful to prioritize our maintenance activities. The weighting method so far still the most common approach for the health index in the industry. Fuzzy logic method has a promising future. In general, whatever the method that is going to be used, it's very important to consider four points. The first point is calibrated health index. So is the developed health index calibrated with respect to time? If you have a deteriorated condition or investigated condition, how much time do you need to take action? And the second thing is monotonic, and with monotonic, a small health index value means good, and a higher health index value means it's more bad for your asset. And there is auditable. If you have a health index, you can understand, or you have a value, a final value, you can look back, you can return back to the raw data easily to identify the changes for the normal value. This somehow is important here with the auditable in order to justify the decisions that will be taken. And finally, the health index should give you a justifiable decision that will help you to identify the failure modes and the components of the transformer that has an issue or a problem. Thank you.
Thank you very much, Mohamed. Everybody, thanks for listening. And if you have any question, please type them in the questions section. In the meanwhile, Mohamed, I have a few questions. First of all, yes, it seems that all this asset health process is, first of all, very difficult, and I think that the expert is needed to do this asset assessment. You described several ways to do the asset health index, and for me it seems that the expert is needed for each and every way that you are doing it. And I think that the first step when you are doing it is to gather all the information that you have on this specific asset and somehow upload it to a software or something that can give you at the end this health index. Is that correct?
Yes. With asset management, to have an efficient asset management for your asset, you need to have efficient tools. You need, when you are in your office, when you are putting your maintenance plan, to have all the available data for your assets under your hands. For the online data, you need to have them somewhere centralized. The same with the offline data. And the health index approach, yeah, I agree with you. It's not easy to implement it. Some of the utilities, they start with the very simplest method, the worst case scenario, and they gain experience. They can go ahead and move to the weighting method, and from the weighting method they decide how far they want to go.
Yeah. Okay. And is there a specific software that you can use in order to calculate this asset health index, or
for the asset health index, we our services team, they are using it. They have their own software system that they are using in order to evaluate the condition of the assets and provide the results to our customers, our clients. Yeah.
Okay, so I think that when a utility wants to start using this asset health index, I think that first of all they need to get some help to start with it, and only after they are trained and have the experience, they can continue it by themselves. Is that a good?
Yeah, that is what we are doing, Eddie. That is one of the things that we are offering to help the electric utilities to start with the best way to manage their data and handle it in the right way, make use of it in their maintenance programs. Yeah.
Okay, so one of Doble offer is that you can start and develop a asset health index system, let's call it, or method for the utilities by gathering the information that they have and training their own engineer, let's say, how to work with it and how to get something out of it.
Correct. Yes, that's true.
Good. Okay, so it was very interesting, Mohamed. Thank you very much. I see that we don't have any question that someone typed in. So everybody, if you have any question, you can send it to us and we will forward it to Mohamed and give you some answers. And again, thank you for being with us today. Again, Mohamed, it was very interesting. Thank you very much for your time. And if we'll have any questions, we will send it directly to you. Just a second. Okay, no, it's only thanks note. So everybody, thank you again. And we will continue with these webinars and we'll let you know what is the next one. Thank you very much, everybody.
Bye-bye.
Bye-bye. Thank you.